Oh wait, right, I have that, my bad. All right, perfect. All right, so key takeaways here, high level, I'm just gonna run over like current capabilities, kind of like what we can do with VR, what we have done with that in terms of research, and then some technical gaps that we have, because there are some things that aren't quite where we'd want it. And then future work, we have planned to address those gaps. So for preface, I work for the EVA and Environmental Physiology Lab. We do a lot more than just VR. In fact, we do basically all of the human research around basically the physical and cognitive limitations of EVA. EVA being any time that you get in a spacesuit and go outside of the vehicle. And there's a lot entailed with this. There's a lot of different test facilities, a lot of non-VR testing that happens, a lot of work in the MBL, the Neutral Buoyancy Laboratory, and other things like that. But we use VR as kind of a tool to do replicable research at a low cost. So this kind of is a high-level overview of other analogs that we use to do training that don't use VR. So we've got like the Neutral Buoyancy Laboratory there is kind of the gold standard of training. That's where we put them in the suit, put them in the pool, and make them run through everything one-to-one. We've also got, we have like field testing that we do out in the desert and out, you kind of see the top picture there out in volcano fields and things. And then we have the gravity offload system there in the middle. That's the Argo system. And all of these environments are really powerful tools for training and research to kind of help prepare our astronauts for doing EVAs. However, none of them are perfect. They all have issues. For example, the Neutral Buoyancy Lab has a lot of water drag. So your physiological data is a much higher workload than a real microgravity environment would be. In Argos, your body is offloaded, but your arms aren't offloaded. And so your workload on the arms is higher than it should be. So basically, all these environments are really cool, but they're not quite perfect. And so our goal was to make another kind of imperfect environment that's low cost and replicable. And that was APACHE. And the idea is let's take VR and try to get things as realistic as we can with treadmills and other things like that, make a realistic physical workload, and do it at a very low cost and make it so we can run a lot of subjects through it and replicate what we're doing. But we will jump on to the next here. So time to get into capabilities of APACHE. We work with a couple different teams at JSC. We work with ER6 as well as Buendia is a company that we collaborate with a little bit. And we use their XOS engine. It's called the XR Operation Support System. We build on top of that, and then it's got a couple different environments. We've got almost the entire moon, essentially, and then we have all the Artemis landing sites at high resolution. So those have all been upscaled to be high fidelity. And then on the right side there, we've got the Jezero crater. And so this is what's used in all of our CHAPEA projects, like Mars-related research and analogs. We're going to jump on to the next here. All right, and then we've got physiological loading tools. And so the big thing here is this is kind of like the secret sauce that's unique to what we do. And this is where we have an analog suit that has been developed separate of this to try to get a realistic workload comparable to what you get from the real suit. And so the idea of this, it has the whole liquid cooling ventilation system underneath, but it's not fully pressurized, so you don't have the risk of getting decompression sickness. And so you can mimic like 90% of the suit physical limitations and weight and CG issues, like where your center of gravity gets thrown off. But you don't have the danger of going into a low pressure environment like you do with a normal suit, because that's where a lot of the risk and cost comes from, is that decompression sickness. And then in the middle there, we use a sandbox. This is where if we want like a really realistic physiological workload while you're walking, I'm sure you guys are probably aware, when you're walking on sand, it takes a lot more work than walking on solid ground, especially if you're in a big, heavy suit. And so we use this when we need the realistic physical workload there. And then we have a 6-DoF motion platform we use primarily for rover operations. We've done some other stuff with it too, but it's mostly used for rover across lunar and Martian terrain. But yeah. Then we've got surface treadmills. So this is kind of one of the more, I think, unique things where we've used VR. So our idea is we don't want to teleport ever. All of our stuff is meant to be as close to realistic physical workload as possible. So that means if we want you to walk 5 kilometers on the moon to go from site A to site B, then we're going to make you actually walk 5 kilometers on a treadmill. And we have a couple different methods to do this. We've got our passive so we have our passive treadmill, which is unmotorized, and the goal of the passive treadmill is very much focused on kind of like how to modulate the metabolic rate, essentially. So we've done a lot of research where we tie work on the passive treadmill to suited work, and so we know that if your met rate is at a certain level on the passive treadmill, then we can equate that back to the suit very easily. And so we use that for when we want the subject to maintain their own pace, essentially. So we're telling them to stay at a certain speed, and then we're checking whether they actually do that or not. The incline treadmill is really interesting. So the incline treadmill will match it to a certain traverse on the surface, and then the incline will match to the incline of the slope in VR. The idea being that if you want them to hike up a mountain at Noble Rim 1 on the south pole of the moon, and you want to know how much physical workload that's going to take 10 different people to do that traverse, you can make them do the real traverse on a treadmill in VR and get the realistic physical workload through like heart rate monitors and physiological sensors. And then we have the omnidirectional treadmill. And so this is primarily in our use case used when you want navigation. Basically, it's like if you want the subject to be able to get lost, then we pull in the omnidirectional treadmill, just because this is a way that it allows them to move more freely. They can kind of sidestep, walk backwards, wander around, spin around, and all of those things are conducive to someone losing track of where they are. And so that's where that's been a really useful tool for some of our research. Right on. All right, so this stuff's really fun. We've got hybrid EVA tools we've been working on. So one of the big things we found is that controllers are cool, they're awesome, they're not realistic, especially if you're trying to train an astronaut or a subject to go chisel a rock with a hammer. Holding a VR controller just really doesn't do it. And so we've been slowly making hybrid tools of all of our VR EVA tools. Meaning that you can essentially just pick up the 3D printed pistol grip tool there on the left, or you can get like the XRF there in the middle, and you just hold the physical tool and it just matches up with the VR tool. It's just tracked, you press the button, it does what you would expect, it's got Arduinos and everything. And essentially this just allows for that haptic feel of the tool. One of the issues we've had is that VR controllers just don't provide adequate haptics, and gloves are really cool, but they don't quite get where we need them. And so the easiest solution right now is to just use things that are shaped as the real tool. And this is one of the ways we've gone about doing that. I did mention tools, so here's some of our VR tools. We've got a good old tool cart, nice and simple. These are all modeled after the actual Artemis tool set, or at least the government reference for it right now. These may change a little bit before we get there, but this is what we're currently looking at. So you got a tool cart to carry everything between sites because tool management is hard and things are heavy. So they use that to roll around. We've got the XRF there in the middle. This is, it's the X-ray fluorescence. I don't know if anyone's aware of this, but it's basically used to ascertain mineral composition of rock samples, among many other things, but that's what we're using it for. And in the VR, we use this as kind of like a little bit of a cognitive tool, but I won't go too deep into that. And then we've also got good old hammer and chisel, pretty self-explanatory. You use a hammer and chisel to break off chip samples. There we go. All righty. Now, so this is one of the things that's really fun. We basically, after we got all these VR EVA tasks where you go do geology, you do navigation, you report how everything's going, we turn them into embedded cognitive measures, meaning that the way that you are performing the task becomes a measure that we can use to grade your cognitive score, essentially. So one of the ways we do this is navigation. We will give a crew member a wrist map, essentially, in their map book that they have on their suit sleeve. And it's very low information. It's basically just a shadow map. That's about it. And then we tell them to go from point A to point B, and they have to intermittently self-report where they think they are on the map and how confident they are in that guess. And then that becomes a cognitive score. And if they don't make it from site A to site B, then that is data for us. That's a failure point, and they just didn't quite get it, and that impacts their cognitive score. So that's one of the things we use. We also use like suit consumables monitoring and a thing called a thermal control valve task. And so essentially in the suit, one of the things they do is they can manage the temperature, like the heating and cooling within the suit to manage their physical temperature. We kind of mimicked that up in the VR where we put a heart rate monitor on the subject. We convert their real-time heart rate into a metabolic rate, and we convert the metabolic rate into a relative suit temperature. And so it's just kind of like a guesstimate of what their current temp is based off their physical workload. So as their workload increases while they're walking between sites or decreases when they're just sitting there taking pictures, they have to change their temperature setting to try to keep their temperature in the central standard deviation is kind of the idea. And so they start at baseline and they want to stay as close to baseline as possible throughout the entire day. And this is just like a background task they have to manage. We don't remind them of it, and if it goes way outside of bounds, like they're plus or minus 15, their baseline temp, then that's data for us to then calculate their cognitive score. We also do geology with embedded tasks. So one of the ways we do this is we have a bunch of different samples at a site, and then the crew members or subjects have to go in and scan all the rocks at the site to figure out what the highest mineral composition is based off the pre-mission brief that we give them. which kind of tells them what they're looking for. And then they get graded on if they did or did not get the most accurate samples and how many times did they have to rescan and all those kinds of things. Alrighty, there we go. Awesome, and then so those were embedded cognitive VR like EVAs that they do. This is embedded cognitive tests, and so these are full-blown tests where we stop what they're doing and we give them a little test essentially. We've got the DSST there on the left side. This is actually taken directly from the cognition battery that Behavioral Health Performance at NASA uses on the astronauts right now as kind of their baseline for cognition. The cognition battery is about a 20 to 30 minute, like really brutal test. We just made a 90-second mini version of it where we took the DSST, you have a pattern matching essentially, whether you just say it does or does not match. It's a true-false paradigm, and we're looking for accuracy and throughput. And so this is a quick test we'll give them before and after a geology site or before and after a traverse to kind of get a quick measure of like, okay, what is your current cognitive score, irrespective of what's going on, just as like a quick number. In the middle, we've got the auditory digit span test. This one is exceptionally difficult, and it's also one of the most useful cognitive tests we have because it always ends in a failure state. Essentially, we will read numbers to the subject with increasing length and complexity until they fail. They have to keep saying it backwards to us. And that'll just keep getting harder each time until they can't do it anymore, and then we know their failure state. And some people can go 9, 10 digits in, and other people can only go 4 digits in. And this kind of equates to their cognitive measure as well. And then on the right one, it's a real simple one. This is just like a quick response time, essentially. It's the psychomotor vigilance is the official term. But essentially, it's just a light flashes, and you have to hit a right or left button, depending on what color it is. And it's just a quick like response time and accuracy, just seeing how you're doing there cognitively. We do also use a lot of subjective surveys. I won't go too deep into these, but these are things that are used outside of VR very heavily. We use these in the Nutribuoyancy Lab, in Argos, and pretty much all of our other human research environments. And these are kind of like, I wouldn't say gold standard, but they're things that we use as comparison data points between different environments. And it's all sorts of stuff from like Bedford workload scale there, for example, is focused on, it was originally developed for pilots. It's very focused on measuring when and where you are cognitively overloaded and when you just can't take anymore, essentially. And then the task load index is kind of similar. That's been around for a long time. NASA's been using that for a long time. It's very much just looking at essentially how overloaded are you on a scale. And then there's like thermal sensation and all sorts of things. But really, this is just something that we pop up in front of the subjects in VR intermittently throughout a long day in a VR sim to get feedback on how they're feeling, how they're doing, and if they're like hitting too high of a rate of perceived exertion or anything like that. But yeah. Now comes the really fun stuff. So we talked about what we can do. Now we're going to talk about how we've used it. So this is research we've done with things. Probably the biggest, most well-known thing we've done is CHAPEA. This is the like 1 year long Mars analog where we have people inside of a habitat for, it's actually more than a year, it's 378 days. In fact, the mission 2 was about to ingress in October. My colleague Alex is currently training the crew down in Houston. But yeah, this is a big study. This is really big. There's a lot of people involved. If you're ever curious to learn more about it, I highly recommend going and checking out Houston. We have a podcast. They do interviews with the crew, interviews with the scientists that set this up. It goes really deep. This is kind of too big of a project for me to really explain the whole thing to you, but the VR part of it is they've got a lot of EVAs they have to do intermittently throughout this long year, and we're kind of grading their performance on how they do those EVAs and how long it takes and mistakes they make on the process. But yeah, that's CHAPEA. A really interesting study we did a while ago is the CO2 contingency walkback study. So essentially, NASA was having like a little bit of an internal debate with some folks where we're trying to figure out where the limits on CO2 should be within the suit, specifically on a contingency walkback scenario. What should that limit be just for safety of the crew? And some people thought it should be no higher than 20 millimeters of mercury, and other people thought you could go up to like 60 millimeters of mercury. No one had enough data to really support their argument. So we sat down, we planned this study where we spent basically, each subject would do an hour-long prescribed walkback on the lunar surface in VR, doing cognitive testing, the DSST and PVTs that I showed you guys earlier, the response time tests. And then we strapped them up with just about every medical sensor we had in the lab. We had Centec, Tosca, Cosmed, a whole lot of other things. And basically, we just used this to measure everything from physiology to cognition and dosed our subjects with titrated in CO2 gas. And so we give them breathing gas and then titrate in certain amounts of CO2 to see what would happen to their cognition and their physiology. And one of the big things we're looking for is where in their body was the CO2 going, where was it building up, like what was their subcutaneous CO2 looking like. If at one point their subcutaneous CO2 is really high, how does that equate to their cognitive score, things like that. Long story short, after this whole study, running a ton of subjects through it, we determined that we could actually bump the contingency standards up higher than we expected. We ended up bumping them up to the 25 to 30 millimeters of mercury range because we found that there wasn't any super concerning impacts. There was some decrements, but nothing that was really concerning. And so we were like, all right, this is safe. Let's go ahead and bump the requirements up. And that ended up leading to new suit contingency standards for the CO2 levels on walkback. This is an interesting study we did called the cognitive workload study. This is probably one of the longer duration in a single day studies we've done. Every one of our subjects spent, I believe it was anywhere from 6 to 9 hours in VR for this study, just for a single run. But the idea was we want to do a long duration EVA that was comparable to a real day, which would be 6+ hours if we were doing this for real. And then we wanted to give them a standardized physical workload. So their physical workload was always the same, it didn't change, but their cognitive workload would change. We'd turn the dials on essentially how difficult were the geology sites they're doing, and how difficult are the certain tasks they're doing. And they didn't know that, but it's one of those things where for them, they're just going through the day, and then we're seeing basically on our end to validate, like, all right, if they're doing bad at a certain geology site, do our cognitive measures reflect that accurately? It's kind of like a study to validate all of our cognition measures. But yeah, this was very interesting. It was a long day of going between 8 different geology sites, sampling all of them, making sure you got the right ones. But yeah, very interesting. And this is also where we use the Infinideck. This is a pretty fun usage of it. You kind of see the video there. I'm in a Buc-ee's onesie because it was Halloween when we recorded this. But yeah. We actually have a currently ongoing study. In fact, I think there's a data collection this afternoon for it, called the CSRM Fatigue and Traverse Study. And for context, CSRM is our crew state and risk model. I won't bore you guys too much with it, but it's a big monster of a prediction model for predicting basically anything physiological on an EVA. And I'll leave it at that. But this study was basically meant to take what we learned from cognitive workload study, where we found cognitive failure points and identified those, and then combine that with a physical fatigue study where we run people up to maximum workload. They're up above 85% heart rate. We've got a medical doctor in the room to make sure everything's kosher. And this study, essentially the timeline, they would go out, they would do an initial geology site as like their baseline cognition essentially, as well as some cognitive testing. And then they would do an initial traverse that was low to medium intensity. And then they would go and do another geology site that was their official, like, this is your cognitive test. And then they do a really high intensity where they go until exhaustion. And we literally just run them for up to an hour or until they want to quit, which I think the furthest anyone made it was like 45 minutes. But yeah, and the goal of this is to figure out, like, okay, we had people at their cognitive limit when they were not working very hard. Now let's have them at both their physical and cognitive limits and see where that line is. Yeah, so very interesting study here. Excited to share results from it eventually. Also, I forgot to mention this, but the cognitive workload study, we haven't published the results yet, but we will be publishing those in a few months. TBD coming soon. Paper's being worked on now. This is kind of an interesting use case of APACHE. This project Perseids was actually another project being developed in the lab that's very focused on decision support for EVA. So essentially the goal was, if we're sending people to Mars, how do you have a system that can autonomously make recommendations for the EVA timeline? Because out of Mars, we can't be talking back and forth with mission control. It's like 20 to 40 minutes delay. It's just not realistic to be trying to help them, so they need to be able to help themselves. And the idea was, can we build a piece of software that off of our big wealth of data on past missions, can we be like, all right, here's the timeline, something just happened, payload was in the wrong spot, now you need to backtrack a kilometer or something. How does that change your timeline, and how do you adjust it to make sure you still get home in time with enough consumables and resources to be safe? That's kind of the Perseids project. APACHE was used to verify that it was working correctly. So we would set up a bunch of different long duration EVA timelines where we run along a long day, and then we throw kind of monkey wrenches into the plan, and then we'd see how Perseids handled it. So Perseids is actually that window on the bottom left there, And really the big thing to note here is that as we're running through this long day in VR, you can see us traversing across the surface, doing all this stuff. It's tracking the timeline and then making recommendations on what we should change, what we should do moving forward, what we need to skip to still make it in time, things like that. So this is one way that we use Apache a lot, is to kind of validate our own internal stuff. We have a lot of software we build for our own work, and we use this to make sure everything's working the way we expect it to. Mostly just because Apache is a really cheap and easy way to run through an EVA. If we were to do this in the neutral buoyancy lab, it would probably cost 6 figures to do one run, whereas we can do this in Apache for pretty cheap. And then one other thing that we did the MarsXR crowdsourcing challenge. We actually did, this is finished up about a year and a half ago. And the idea of this was to basically get more content from the community and get more people from the community involved with what we're doing. So we kind of open sourced, at this point now, kind of outdated version of our engine, but we open sourced a version of our engine with the Mars maps and everything. And then basically put prize money on the table and had a bunch of different people compete to develop different EVA tasks for us. And basically these are just different ideas that we could then use to then funnel into CHAPEA as extra things for them to do. This was a really great way to like connect with different people in the community and meet a lot of interesting developers, kind of build up like a network of people we can like talk to and work with. I know it's helped me a lot. But yeah, so this has been really great. Alrighty, so high-level conclusions. So there are some limitations, obviously. I think I hit the biggest one for us is really haptics. The controllers and gloves are awesome, they're super cool, but they just don't quite hit the realistic haptics of what we need. And so that's where one of the things is like we've really been reworking to just use the real tools as much as possible or use hybridized versions of the tools like I was talking about earlier. Just because that allows you to, by default for free, you get the haptic feel that you need, and then you kind of get that muscle memory training. Another limitation is eye tracking. We do currently use eye tracking on a bunch of stuff. We use it for like long duration cognitive fatigue monitoring as well as a few other things. However, some of our favorite headsets don't have it. So I haven't gotten deep into headsets, but we do use a Quest 3 just because it fits well with our mask. We have a metabolic monitoring mask that we use, but it doesn't have eye tracking. So we also use Vive XR Elite, Vive Focus, Vive Pro Eye, a couple other things. We kind of throw all the headsets at it. Based on what we need. But that is one gap, is lower profile headsets that still have the eye tracking involved. But yeah, I think that's kind of the biggest gaps that we really have to work with there. Let's see, what else? Yeah, so summary. I mean, I guess I kind of, I want to talk your guys' ears off. I want to leave some time for Q&A, so I'll just leave this up for a bit. But really the big thing is we talked about capabilities, how we've used them. We've got some gaps, and we got a lot of ideas for how we want to fix them moving forward, but curious if you guys have any input. With that, I think I'm ready for Q&A.
So actually what we're going to do, Caleb, first of all, thank you. That was tremendous, so a lot of fun.
Thank you, thank you.
So I want to let everyone know lunch is now open and available. I'm hoping Caleb can kind of hang out and take some questions from all of you. But if you want to go to lunch, you can. A couple reminders again, we've got the networking prize drawings that's going to take place at 1:50.